So, hello everyone. So, today we are starting week 10 that is bioprocess instrumentation and control. So, we will quickly recap the last module. So, we discussed heat transfer in bioprocessing. So, we discussed different mechanism of heat transfer, the conduction, convection and radiation, and we discussed that in bioprocess mostly this conduction and convection are more relevant. Then followed by that we discuss cell death kinetics that typically follows the first order kinetics. Then in the next lecture we discuss different way to go for batch and continuous sterilization. In addition to that we also discuss the air sterilization. Then in the next lecture we discuss few heat transfer equipment, particularly this cell and tube and double pipe heat exchangers. So, what is important for having a good heat transfer equipment is to increase the heat transfer rate. So, let us say if you follow the convection. So, convection says Q equals to U A delta T. So, the overall heat transfer coefficient need to be maximized, the area contact area need to be maximized and delta T. So, typically the heat transfer equipments are designed in such a way to maximize the contact area. For example, if you remember the cell and tube heat exchanger, it can be single pass, it can be multi pass to increase the contact area. And followed by that we discuss another topic, that is the bioprocess scale up. So, here we translate the lab scale result to the production scale. So, from lab scale to pilot scale, then to production scale. So, there we try to maintain this geometrical and this hydrodynamic similarities. So, further different criteria were discussed, like equal aspect ratio that comes under the geometrical similarity, and other criteria where there this constant power per unit volume, constant Reynolds number, constant tip velocity, constant flow per unit volume. So, considering these, what we to discuss that one need to calculate as well as based on the experience one can decide which scale up criteria need to be this adopted and tested. So, in today's lecture the first topic will be the sensors for bioreactors. So, in this lecture we will be discussing first why we need to go for bioprocess instrumentation, how it is relevant, what is its importance. Then what are the parameters which we are going to monitor. So, basically when we say instrumentation means we are going to monitor certain parameters. So, those parameters we are saying type of parameter means it can be classified as physical parameter, chemical parameter as well as biological parameters. Then what are different type of instruments which are applied to monitor these parameters. So, why you need to monitor? As you know, for let us say for a bioreactor the optimum temperature is let us say 30 to 40 degrees centigrade. So, unless and until someone monitors the temperature, then only one can maintain a optimal temperature. The same may be true with this dissolved oxygen level. If you know the DO, then only you can ensure the sufficient aeration rate is being maintained. So, the whole idea is to maintain the optimal condition which is required for your bioprocessing, for example, microbial growth, substrate utilization and product formation. So, how we can maintain the optimal condition? For that we need to monitor these parameters like temperature, pH, dissolved oxygen and other parameters. Now, once you are going to monitor, so there are certain probes that need to be inserted in your bioreactor. So, once you are inserting those probes or taking out the sample to monitor these parameters, so there is some issue of this sterility, because there are not many online sensors are available. So, we have to withdraw the sample and do the analysis. So, this is the challenge that also will be highlighting in the next slides. So, monitoring and control of bioreactor. So, as I discussed earlier, the bioreactor must maintain optimal catalytic activity or optimal biochemical reaction for both fermentation and biochemical reactions. And what are the key parameters? I have listed a few here. Let us say temperature, pH, dissolved oxygen, liquid flow rate, this stir speed, sparging speed. These two are relevant for the aerobic culture. Then once you know these are the parameters, you need to monitor then and control them. So, first thing you need to monitor, then only you can control. So, monitoring and control ensures deviation from the desired value are corrected. So, let us say we keep a set temperature. Let us say set temperature is 35 degree centigrade. So, once you are monitoring the temperature, if it becomes 40 degree centigrade, it means you need to go for the cooling, and if you are measuring it coming down to 30 degree centigrade, then you need to go for the heating. So, heating and cooling, that is the control step, and first measuring this 35, 40 and 30, that is the monitoring step. So, as I told, there are not many sensors available for online monitoring. So, fermentation monitoring is a research topic or research focus for improving the performance and consistency of bioprocessing. So, this control will be the second part of this module. So, there we will be discussing that how we, after monitoring, we can go for manual control, we can go for automatic feedback control, or we can go with the advanced computer based control. Manual control means one can switch on and switch off the pump, motors, open and close the valve. Feedback control, it will compare your monitored parameter with the set point, and accordingly a decision will be taken by the controller. And advanced computer based control, so it directly uses this input from your computer. In the real time we are able to give input and it will be able to correct it. Now, what are the parameters which are important in bioprocessing, and these parameters can be classified as physical, chemical and biological parameters. So, there are many, but it is not possible to monitor and maintain all the parameters, but I have listed most of them here. For example, in case of physical parameter, temperature is important parameter. Next comes the pressure, the reactor weight, or you can say working volume, liquid level, again it is related with working volume, foam level, this is not desired, but if it is there, some corrective measures need to be taken. Agitation speed, what is the RPM, that need to be maintained, and if you are having this agitation or mixing, you need to monitor the power requirement. Gas flow rate, particularly in the case of aeration. Liquid flow rate, you are working with continuous culture or you are working with the fed batch culture, you need to continuously or intermittently feed the substrate. Culture viscosity, what is the flow behavior, if it becomes too viscous, then it causes mass transfer resistance. And gas hold up, this is the criteria we have already discussed during the aeration lecture. So, these are the physical parameters that one can monitor. In the case of chemical, the important one is pH. This is very important, and in most of the cases pH probe is available in a bioreactor, and dissolved oxygen probe. So, these two are the very important and mostly available with any lab scale or the production scale bioreactor. In addition, the dissolved CO2 is also monitored, redox potential, composition of the exit gas, conductivity and broth composition. By measuring the substrate, one can measure the rate of substrate utilization. Measuring the product, one can monitor the rate of product formation, even one can monitor the ion concentration which are added as a micro or macronutrients. Similarly, biological agents and biological compounds also can be monitored, and the first one is the biomass concentration, second comes the enzyme concentration and enzyme activity, the next comes biomass composition, such as one can monitor its DNA, RNA, protein, ATP and NAD levels. One can monitor the cell viability, how many live and dead cells are there, what is the morphology of the cells, whether there is change in the cell morphology during the course of fermentation. Optical density, this is another method to monitor the cell concentration. We have discussed this in the previous module, where we are discussing how to monitor the cell growth. So, there we have discussed the optical density method. Typically, we go for OD at around 600 nanometer to monitor the biomass growth. Then metabolites, what are your products that can be monitored. So, these are the various biological parameters which can be monitored, and once they are monitored, then control is possible. For example, if you are monitoring the substrate, then you are able to do this intermittent feeding as and when required. If you are monitoring the product, you should be able to regulate the product inhibition if it is present. Yeah, here is a schematic. You can see you are having a bioreactor and that is attached with different probes. To first you can see the pH control, then the foam control, then agitator and power, then spurger is there for the air supply. This will monitor the gas flow rate. This is circulating water bath with circulation pump for the temperature control, and this is a dissolved oxygen control. Directly probe is there and exit gas is going out, so that can also be monitored. So, typically you see this is agitation, this part is agitation, this is the aeration, and this is pH, foam control, this off gas control, dissolved oxygen control, and this is to control the temperature. We are having water bath with a circulation pump, and there can be whatever I have discussed in the last slide. All those parameters can be monitored, but as I discussed earlier, then it can be very complex, and it is not possible to have this all the sensors to monitor them. In addition, it is also important that all the parameters need not be monitored and controlled. Now, once you are having these different sensors, they can be classified into three categories: inline, online and offline. Inline means sensor is an integral part of fermenter and measurement value is directly used for the process control. So, once you are having inline sensor, it will, you say you fix the set point, it will automatically keep working. Online sensor is an integral part of fermenter and measured value is manually entered for the process control. So, you are seeing the measured value, then you need to enter and then accordingly controller will work. Offline sensor, here the sensor is not a part of bioreactor, it is not directly integrated or attached with your bioreactor, and measured value cannot be directly used for process control. So, in this case you need to take out the sample and then analyze separately. For example, biomass concentration, if you are taking out the liquid and analyzing, or the product and substrate concentration from the broth sample. So, you take out the sample, analyze, then you understand what is your biomass concentration with time, what is your substrate concentration with time, and what is your product concentration with time. Now, here this is important consideration, because once you are going for measurement, it takes certain time, and as you know, all these parameters are the dynamic parameters, means these parameters keep on changing with time, because this is a live process. So, it is important that time taken to complete the measurement, it should be consistent with the rate of change of the variable being monitored. Let us say if you are monitoring the biomass concentration, if it is taking too long till the moment you got the result, it has increased or decreased further. So, this monitoring cannot be used for the control purpose. So, this is very important, that what is the time required for the measurement, that should match with the rate of change in that particular process parameters or variable. Now, we can classify the instruments also in different types. We can say the basic sensors, advanced sensor, and real time monitoring tools. Basic sensors, typically we categorize temperature, pressure, pH, dissolved oxygen measurement. For example, thermocouple is used for temperature measurement, pressure transducer is used for the pressure measurement, is a pH probe for the pH measurement, and DO electrode for dissolved oxygen measurement. In addition, there are advanced sensors. One can have the fluorescence sensor for monitoring the cell viability. One can have this mass spectroscopy or off gas analysis, near infrared spectroscopy for biomass and metabolite monitoring, and one can have the biosensor, because biosensor are very much specific for a particular compound. It may be your substrate or it may be your product. And next one is the real time monitoring. So, as I told, one can enable the dynamic control and optimization of bioprocess if it is inline and this online monitoring, so that whatever measured value is coming, that is displayed in the real time, and the same can be utilized for the optimization and control purpose. So, here we are going to discuss some of the physical, chemical and biological parameters. What is its significance, what are the different methods to monitor them, along with a few remarks. For example, temperature. What is the role of temperature? Because all the enzymes and even microbes, they have optimal temperature. So, it affects the growth rate as well as the enzyme activity. And how typically it is monitored? Using thermocouple, resistance temperature detector, RTDs, and thermistors. So, it says for the small size and rapid response, thermistors are mostly used. Agitation speed, if you are having this aerobic culture which is having both aeration and agitation. So, this speed ensures the mixing as well as the oxygen transfer, so that there is no dead zone inside the bioreactor. It also ensures the uniform mixing, and it can monitor by having this motor speed sensor. So, what we are monitoring? We are monitoring typically the RPM. Agitator soft power, how much power is required. So, it indicates the energy required for the mixing. So, for that wattmeter or strain gauges are available, and typically these strain gauges are used in the bench or pilot scale equipment. Next comes If it is aeration, the gas flow rate, it controls the aeration, it also indicates about the CO2 stripping. So, for that mass flow controllers are there, for example, rotameter or thermal mass flow meter. So, how does it works? Rotameter basically works on the Bernoulli theorem, and it says the position of rotameter throat is converted to an electric signal, then the controller manipulates the flow valve. So, in this way the monitoring and control both take place. Similarly, liquid flow rate to maintain the nutrient supply and ensure the dilution. So, for that turbine meters are there, magnetic sensors like magnetic inductive flow meters. Another option is to measure the change in the weight by simple load cell. So, that change in the weight it gives how much liquid is coming inside a bioreactor. So, magnetic inductive meters are good for viscous fluid or fluid with high level of viscosity. Another parameter in the physical, another physical parameters are the foam level, pressure, liquid level, and let us say off gas. Foam level, why we need to monitor the foam? Because if the foam will be there, the reactor will overflow. So, it prevent the overflow, as well as once it is overflowing, most likely it will get contaminated. So, for that the foam probe are there, rubber sheathed electrodes are there, and level detectors are being used. So, how it works? Let us say you are having mechanical foam breaker, they are safeguarding. One option is there you can have the sensor to activate the valve to release some anti-foam agent. Pressure, it maintains the safety, it maintains the gas solubility. We have discussed, following the Henry law, the gas solubility is proportional to the partial pressure. It is important for the sterilization and asepsis, because there should be positive pressure inside a bioreactor. How it is monitored? There are pressure transducer or diaphragm gauge. So, pressure is regulated by a simple back pressure regulator in a gas exit line. So, in the gas exit line you are having a regulator, and using that regulator you are able to control the pressure of the vessel. Liquid level, it indicates the working volume. So, for that one can have the load cell to measure the amount of liquid in the vessel. You can monitor the liquid height, conductivity sensors are there, capacitance probes are there, and ultrasound based sensors are also there. So, liquid height is the easy to monitor. So, liquid height is a function of gas discharge rate and gas hold up, but the foam can complicate the measurement of liquid height, it will not give the actual value. Exit gas, it says off gas generated during the bioprocessing. Typically mass spectrometers are used, and here the issue is only volatile components can be monitored using this technique. Now, see few chemical parameters like pH, dissolved oxygen, viscosity. So, pH is very important, it influences any biochemical reaction. So, it influences metabolism, it influences the stability of your product, and the most common one is the pH electrode. So, as I discussed earlier also, the online measurement is possible using pH electrode, but it is specially designed to facilitate a repeated autoclaving, because we need to reuse it. So, once it is inserted in a bioreactor, there are chances of protein fouling of diaphragm, and that can be a challenge. So, the fouling is another problem. there, particularly in the case of online measurement. Dissolved oxygen, this is very much critical for aerobic organisms. It also indicates the cell viability and productivity. So, we go for this polarographic or galvanic electrodes or optical dissolved oxygen probes. Again, this is used for online measurement, and typically this partial pressure of oxygen is measured, not this oxygen concentration. The response is slow. So, there are some challenges like drift, fouling, and once there is a drift, one need to go for the recalibration. Next comes the viscosity. It is indicator of flow behavior, whether it is a Newtonian flow, non-Newtonian flow, and typically this rotational viscometer is used, but here the online measurement is difficult, and so we need to take sample and go for this offline measurement. And broth with high solid content, they creates another challenge to measure the viscosity. Here I have listed few biological parameters as well, like nutrients and bioproduct level. So, this is important for optimizing your feeding and avoiding the substrate and product inhibition. So, many, as I told, biosensors are very much specific to a particular compound. So, different biosensors can be used, or NIR spectroscopy is applied. So, there are some challenges with both biosensor and NIR spectroscopy. The significant technical advances to be made to make these biosensors and these methods readily applicable for large scale application. Biomass and metabolites, so they are biological agents and product. So, we use optical sensors, biosensor and spectroscopy methods. So, in this case, the spectroscopy analysis combined with optical fiber may offer a good technique to determine the cell mass even in the presence of other suspended solids. So, spectroscopy methods are quite powerful and they are applied in the bioprocess monitoring as well. Turbidity, this is another method to indicate the cell mass. So, for this we use the photometer either as a probe into reactor or in a slip stream. So, it has many problems, particularly fouling and interference from the gas bubble and suspended solids, because even if you are having the culture of let us say fungus, it is difficult to measure the turbidity. This method works well as long as you are working with bacterial culture. So, now we can summarize what are the challenges we face. The first challenge, if you increase the number of probes, so you are compromising with the sterility, and second is the whatever probe you are using, that should be sterilizable and that should be reusable. And as I told, online measurement is mostly used for the pH and dissolved oxygen, and the same need to be this developed for other parameters. And when you go for this different probe in a bioreactor, the probe fouling is another challenge, because we go for the extended fermentation. Fermentation can go up to a month. It start with the days, it can go up to a month. So, there will be some biomacromolecules, let us say protein. So, they can get deposited on this probe surface, and then it interferes with this monitoring. Yeah, drift is another problem in some probes, and for that the recalibration need to be done, and recalibration in situ is not always possible. So, what are the recent developments? Recent development says this: for the remote monitoring and control, this IoT integration is being explored, Internet of Things. In addition, for predictive analytics and process optimizations, nowadays artificial intelligence and machine learning are being exploited. And when we are discussing about this biosensors, so there these nanomaterials are being tested and for enhancing the sensor sensitivity and specificity. So, why it is important to go for this bioprocess monitoring? Because it enables the high throughput data acquisition. Once you are having those data, then you can decide to go for a good control and go for optimization. It ensures the precision, and once you are able to control, then you can ensure the reproducibility. Further, if you are able to monitor, it facilitates the real time decision making, whether which parameter to control and how to control. For example, temperature, whether you need to go for cooling or you need to go for heating. And once you are having this monitoring and control, it supports the scale up from the lab scale to the production scale. So, what we have discussed is the bioprocess instrumentation is very essential for optimizing biotechnology process and integrating modern technology for enhanced performance. Because still you maintain the optimum condition, you are not able to improve your productivity and achieve the desired results. So, with this I will stop here. Thank you.